how much flexibility
Last time I said to you in the bar,
these
I
are
think it's
attacks
sore.
like quite hard, but they have
And you
If you destroy the tower, what's happening next?
and
you need to buy
the one who has no tower, yeah, left. When the time runs out, it's
Carbon with expensive carbon.
really hard. The tower is yeah. It's really nice. How can I have
Okay, so I finished the last lecture talking a little bit about the fact that although the structure of steel directed by thermodynamics is fairly well defined by the phase diagram, in real systems we have to take into consideration the cooling rates, because these transformations don't take place immediately. And the reason that we're interested in this is if you think about a welding cycle, we have a welding torch which heats the material up from room temperature to the melting temperature of the particular material, so in steel about 1500 degrees C, and then the material has to cool down. Now, unlike in a conventional heat treatment furnace where you put the whole component into the furnace, with a welding process you're only heating the area around the weld. So there's a lot of metal generally around the welding region that can conduct the heat away. So the cooling rates that we tend to achieve in welding are much, much higher than you would normally achieve in thermal processing in industry. And as I mentioned before on this diagram here, if we start off having heated the steel up to more than 900 degrees C so that it has become the austenite phase, if we cool quick enough, we cool down here, we get into this range here where we have this M phase, this martensite phase that's forming. And the reason that that's a problem is that martensite is a very hard and brittle phase, and it doesn't look anything like the ferrite and pearlite that we showed originally. So martensite is a non-equilibrium single phase structure, and it's formed by a diffusionist transformation. You don't need the atoms to hop from site to make martensite. You shear the whole structure and you move the atoms in a mechanical fashion, and that transformation can happen at the speed of sound in the material. So you're shearing the material to make this martensitic structure. And what's happening is, as you cool the material down quickly, it hasn't got time for these diffusion reactions to take place. So it hasn't got time to make equilibrium microstructures. And the energy that would normally drive the phase transformation goes into mechanical energy to drive this diffusionless transformation. So if we quench quickly enough, we'll get martensite, but if it's not quite so quick, you can end up with pearlite and bainite structures which are much more like the thermodynamically stable phases. They're a mixture of ferrite, pure alpha iron and iron carbide. Martensite looks very different to the ferrite and pearlite structures that you might have seen in the previous slides. It has a needle or plate-like appearance. In fact, it's very difficult to see anything unless you've got a very high magnification microscope, because it happens over very small areas. So just as an example, so this is martensite, and this is a similar low carbon steel to what was shown previously, where we had white grains of ferrite and then regions of pearlite. So this looks nothing like that. It looks perhaps like looking down on a mountain range from above. So you get these needle-like crystals that you can just see, almost like trees that are knocked down on the mountain slopes or ridges in the mountains. Actually, if you take an individual unit of martensite, it looks a bit like a lens from your spectacles. It's thin at the edge, it gets fatter in the middle, and it's thin at the edge. And it looks like a disc if you look down on it, but it looks like a needle if you look across. So that's why you might have concerns that this doesn't behave anything like ferrite and pearlite. It's all one phase. It doesn't have the ductile ferrite and the brittle but strong iron carbide. In fact, the whole martensite phase is brittle but strong. And in fact, it's even stronger than the iron carbide, which means that it's likely to be the cause of problems if it forms in the system. And how do you form it? You form it by rapid cooling from material that's been heated into the austenite phase. So if we cool austenite quick enough, you get that. If you cool austenite not quite so quickly, then you can get some thermodynamic phase changes. So this is an example of a steel that's cooled a bit slower, and you can see these white grains here of ferrite, and we can see dark regions in between them, and that's pearlite. So that's almost like the structure we would expect thermodynamically with slow cooling. But we get regions in here, which if you went to a higher magnification microscope, or if you put a little hardness indent in to measure its mechanical properties, you'd find that's very hard. And in fact, that's not pearlite, that's martensite. And you get regions like this white region here, which it looks like ferrite, but again, if you put a hardness test in, you'd find it's harder than ferrite. And I don't know if you can see, it's got very small spots inside it. It's got very small particles of iron carbide in the ferrite, and that's a bainite structure. Mr. Bain was another metallurgist of repute about 70 years ago, so he had something named after him. And in fact, the strain that causes the transformation from austenite to martensite is sometimes called the Bain strain, after the same person. So it's perfectly possible to have the same material show two totally different microstructures just depending on cooling rate, and it can have really brittle phases and really ductile phases mixed. So as far as we're concerned, what we want to do is get rid of as much of the martensite as possible. So we need to know a little bit about what the conditions are for making martensite. So we have to heat the material up to 900 degrees C or so that we've got complete austenite. That's the first condition. And then the second condition is we have to cool fast enough to miss the transformation to the thermodynamically stable phases, second condition. Then as we cool down, we have to get to a certain temperature before martensite will form. And we have a couple of temperatures here. The martensite start temperature, so that's the highest temperature that you will form martensite at, and the martensite finish temperature, which is when you get 100% transformation, and that's at the lowest temperature. And what we've plotted here is those temperatures against the amount of carbon. So for a very low carbon steel, then martensite actually does start forming at high temperatures, more than 500 degrees C, and it finishes by the time you get down to 400 degrees C. But as we increase the amount of carbon, the temperature which you start and finish the formation goes down. So typically gears and bearings have 0.8% or just a little bit more than 0.8% carbon in. So the martensite start temperature is now about 300 degrees C. So we have to cool rapidly from 900 to 300 to get this. Martensite finish temperature is less than room temperature. So what does that mean in the structure? That means we started with austenite, we've converted some of it to martensite, but at these very high carbon contents, we can't convert some of the austenite. So we end up with austenite stable at room temperature called retained austenite. And you have those in gears and bearings and cutting tools. And if you want to get 100% martensite, you've got to stick this in a deep freeze. So there are processes, heat treatment processes that involve deep freeze treatments or cryogenic treatments of the material to get 100% of this hard phase, if that's what you want. Now again, if we look at mechanical properties, this is two different hardness scales, Rockwell C hardness scale and the Brinell hardness scale. It doesn't matter what the definition is. Basically, the higher the hardness, the higher the strength of the material. Again, we've got composition across the bottom, and all we've plotted here is the hardness of perlite with a small grain size and the hardness of martensite. And it's immediately obvious that martensite is much harder and therefore much more brittle than the perlite. And the difference is relatively small at low carbon contents, but as the carbon content goes up, martensite becomes much, much more harder. Now, typical construction steels with around 0.2% carbon go from about 100 to about 400. So it's a factor of 4 increase in strength. And that has a consequence in brittleness by forming the martensite. So if you can slow the cooling rate down to stop martensite formation, then that's a good thing to do. And you have to bear in mind that it's very difficult to slow down the cooling rates actually with welding unless you do something like heating the material around the weld, either a preheat or a post-heat treatment. And that's one of the reasons why that's done. And it's to prevent martensite formation. So what you're trying to do is stop getting the brittle martensite if you possibly can. So what do we got? If we go back in sort of summary to microstructures for pipeline steels as a function of time. So the hot rolled, fully killed steel, which is the one at the top here, has large grains of ferrite, has quite a bit of carbon in it, so there's large regions of perlite. It recrystallizes during the rolling process, and it's not directional. The microstructure is random with direction. So we go to the fully killed and normalized steel. So normalizing means that we heat to 900 and allow to cool in air. So that's a relatively fast cool, but it's not fast enough to make martensite. And what you can see then is the microstructure is actually the same, except the grains are smaller. And again, because this has been normalized, heat treated, it's a fairly random microstructure. You can't see the evidence of the rolling. This is a controlled rolled fully killed steel, and you can see that the microstructure lines up in bands. This is the rolling direction here. So we sort of squashed and smeared the microstructure out in the direction it's going through the rollers. So you end up with bands of microstructure, but the grain size is even smaller, and you've got smaller regions of perlite in between those regions of ferrite. But you can almost see there's a ferrite band here, and then there's a perlite band, and there's a ferrite band. And the easiest way to tell if you've got rolled steel plate is to look for this banding in the microstructure. And even with the naked eye, if you etch the surface, you can sometimes see that structure. It's very easy to see. And certainly with a low power microscope, you can see that.
On the top image, it looks like the grain size is a lot smaller towards the top of the image.
It is, yes, yes.
Position against the rollers.
This was quite a thick plate, and a lot of the deformation is done by gripping with the roller, so there's a lot more shear next to the roller than there is in the middle of the plate. Because pipe steels tend to be quite thick, you do get this gradient of properties across the material. If you're talking about a car body sheet, which is also cold rolled, it's only a few millimeters thick, you don't see this variation. Okay, so we've got these different materials that have been developed over different periods of time, and they've got mechanical properties that vary, and you can compare different ones. And this is a case just where we're comparing the drop weight tear test shear area, so it's assessing the ductile to brittle transition behaviour of the different materials. So if we start off with a semi-killed old steel X52 grade, the temperatures over which you get the change from ductile to brittle are around 20 degrees C. So that can go brittle just by a cold day, and that's not a good material for making anything out of, really. So if we fully kill and normalise it, so we've got the stripes going in this direction, the temperature drops to -30, -40 degrees C. So suddenly, by changing that manufacturing process and getting rid of the impurities and things like that, you've done a very good job at improving things. Now, as you increase the grade, material becomes more brittle, and in this particular case you can see there's a movement in the ductile brittle transition temperatures to higher temperatures again, but it's still well below 0, so it's still pretty good under those cases. Going from the fully killed structure, which is this one here, the controlled rolled one with the finer grains is actually pushed the temperature back down again. So that's good. That shows you that the smaller grains actually improve the toughness in the material. But it depends. The bigger change has been going from the semi-killed to the fully killed steels, because we've got rid of the impurities that have been responsible for this. So, controlled rolled steels have high strength because of their small grain size. They have a degree of cold work. You've plastically deformed them, you've rolled them, and that means that there is some work hardening contribution to that strength as well. And that will disappear, of course, when you weld it. So bear in mind that. And generally, there is some sort of microalloying that produces very small precipitates of a carbide, vanadium or niobium carbide, to give you even better properties and to stop the grains from growing during the thermal process. And again, if you've got small grains and it goes through a welding cycle, those grains are pinned by those carbides, except right close to the weld pool where the temperature gets high enough that the steel will dissolve the carbides. They have excellent toughness. Again, small grain size. That's what you want to do. But we've improved the non-metallic inclusions in the system. We've reduced the amount of sulfur, we've reduced the amounts of bits of aluminosilicates, and we've cleaned up the steel making process, basically. And good weldability, because the carbon equivalent is low. We haven't had to add carbon to increase the strength. We've increased the strength by reducing the grain size. And therefore, we don't have to worry quite so much about martensite formation, because the thing that promotes martensite formation is the amount of carbon that's in the steel, or the carbon equivalent. So we keep that as low as possible. So we've got a good material, and we've controlled it by the steel manufacturing process to give the properties we want without putting extra alloying elements in, which can be detrimental. So processing is very important, and you can compare different processing systems. So what we've got here is yield strength, the onset of plastic deformation, plotted against the carbon equivalent for different steels. And then in the bands that you can see up here, there are different manufacturing processes that could be used in the steel making to generate the standard that you want. And I've drawn a line here for X80. So you want to be above this line if you're going to deliver X80 steel. So if just normalized steel, where we just have a cooling from heating to 900 and then cooling in air, the strength goes up with carbon equivalent, but it's not actually a very big change, and it's below the standard. So just by simple normalizing, you can't make X80. By controlled rolling, we can make X80, but only at high carbon equivalent. So the next one up, if we put the accelerated cooling in, we can drop the carbon equivalent where we can get the X80, which is what you want. And finally, if we do a quench and tempering experiment, which is what you might do if you're trying to make a martensitic structure, we can certainly make the strength requirement. Carbon equivalent can be quite low under those cases, and you can be, if we put the quenching process in, that can meet the X80 standard across the board. There are no pipeline steels that are made by quenching and tempering, but you may want to quench and temper a finished pipe in order to restore its properties after welding. So the quenching process makes the martensite, the tempering heating process afterwards gets rid of the martensite and gives you a microstructure with high strength and toughness. So generally we're in the accelerated cooling range, and we're with carbon equivalents between 0.3 and 0.4. And that's a sort of way that we can achieve the X80 standards. So that's the sort of things that the industry has been doing over the years, looking at the various possibilities, processing that can be done, seeing what effect it has, plotting them against a standard, a target, and working out the safest way to achieve that target. And as I say, the accelerated cooling is essential to get reasonable quality X80 for this reason. If I was to put X65 down here somewhere, you can achieve it just with controlled rolling. So X80, why are we focusing on that? There has been a big drive towards incorporating X80 on terrestrial onshore applications for gas pipelines. And in particular, the big distribution spines that take gas around the country, large diameter pipes tend to be made with X80. And the reason that we tend to use X80 is that it's got a relatively small wall thickness compared to the other grades. It's easier to transport, easier to move around, easier to join if you get the procedures right, and you can put more gas through, which is for productivity is very, very important. And the quality of steels available has got sufficiently good that it's now usable. So at least in the UK, as far as I'm aware, X80 is about the limit that you're likely to find for a pipe order in terms of the strengths that are around. There are higher strength pipes in Canada and places in the Far East, but we haven't gone that far yet. So why are we developed X80? Well, it's got now quite low carbon content because we want good weldability. It's got quite high manganese content because we want good strength, and that helps to deal with the sulfur and these other impurities. There's titanium microalloying at a very low percentage, 0.02%, and this is used for getting good heat affected zone properties around the weld, particularly in the seam weld along the length of the pipe. What titanium can do is it can preferentially get a carbon. It can react to form carbides there in thermal cycles, and so you can restrict the amount of martensite formation for that reason. There are low impurities. Sulfur is controlled, phosphorus is controlled, oxygen is removed in the steel making process as best we can, and nitrogen is controlled by the killing of the steel, and that gives us good ductility and toughness. We control the rolling conditions and the cooling conditions, accelerated cooling, as I mentioned before, to get the right sort of strength. And we can get the material from multiple suppliers so that you're not tied into a high-cost single supplier degree. So when there's competition in the marketplace, when they can meet the standards and produce material which is usable for your particular job, then you tend to get the best performance overall. Carbon equivalents are all about the same, but there's slight and subtle differences in the other composition, because remember that X80 is delivered against a strength specification. It's not delivered against the composition specification. So the Europipe standard and the Nippon Steel standard differ, if you look, in the amount of nickel and molybdenum. In the Europipe specifications, it's as lower alloying element content as we can get, pretty much. Whereas the Nippon Steel, they still require the nickel, molybdenum, niobium content. They've dropped the manganese content a little bit. And the Ilva composition is somewhat different, and they've achieved things with less manganese but more of these other alloying elements. But the key point, if you look at it, is this carbon equivalent, which is effectively the weldability measure, in this case, is the same. Compositions are different, strengths have been achieved to meet the standard, but how you do that is up to the choice of the supplier, and there are different ways, as the English thinks, there are different ways to skin a cat. So you can achieve the same result, but by different approaches. So these will be processed in different ways, and I don't know what the differences in processing are, because that's proprietary information from the steel companies. So, one thing I do know is that when you get same material and put it through a process, and then you add an accelerated cooling to the process, so this is effectively the same composition of material, we can go from an X60 grade to an X80 grade. We've got a ferrite perlite structure here. You can see the dark regions of the perlite. This looks pretty much the same. We've got ferrite grains, we've got dark regions, but if you go in with a high power microscope, you'll find this is bainite. Instead of having plates, lamellar sheets of iron carbide, it has little precipitates, little dots of iron carbide. But you need a pretty powerful microscope to actually be able to see that. And that's what's happened. This is a 50 micron, so the grain sizes in here is going to be of the order of 10, 20 microns. The grain size here is 10 microns less, or less. And so we've achieved everything really by accelerating the cooling. And what accelerating the cooling does, even if you don't form martensite, it prevents grain growth and it keeps the microstructure small. So the advantages of X80, as I mentioned before, lower line pipe cost per meter. You're buying less material. For the same pressure, you need a thinner wall pipe, and therefore you're buying less material. And that doesn't sound very much. You might be saving, pennies per pipe in terms of material costs, but when you've got 150 kilometers of pipeline, and each pipe element's 12 meters long, you save pennies for each 12 meters. You're saving many pounds and many thousands of pounds on the full pipe order. That's why people will do it. You also save on transportation costs, because a thinner pipe weighs less. You can get rid of smaller lorries to deliver things. You need less cranes, less powerful cranes to actually lift things on and off. It becomes a lot easier. If the wall thickness is smaller, you can get away with less passes in the weld, so you get reduced welding and construction time. Also, that is because you use smaller cranes, it's easier to manipulate the lighter weight pipes. And as I said, the thing that the the accountants often like is the larger diameter to thickness ratio for these things tends to mean you can get slightly more gas through the pipe, and that means more money can be made for the same pipeline. So of all these advantages, that's great, but of course there's some disadvantages. Possible increased failure frequency. You've got less margin for error with a X80 thin wall pipe than you have with an X65 pipe. If somebody comes along and drives a car into the pipeline or something like that, or earth moving equipment digging a trench for some other utility, hits the gas pipe, got a more chance that that's going to be a fail. And we keep databases of failures in pipelines, the transmission companies do, and we've got the indications that there are a higher failure frequency with X80 pipes than with the other pipes, but there aren't that many X80 pipe failures, so we can't really tell yet whether that is going to be true in the longer run. But generally, as we increase the grade, the failure frequency increases. I said that these pipes can be welded. They can. The procedures are a little bit more complicated to follow. So you need to have slightly better qualified welders, particularly for manual welds in tie-ins and things. And the one that often gets forgotten is a larger diameter to thickness ratio. The pipe is small. That gives you reduced structural stability. So if you imagined a beer can, when it's full of fluid, it's fine. But if it's empty and you squeeze it from the outside, you can get elastic buckling. So you can actually crush the can. You let go, and it will jump back out again. And if you squeeze it too much, you can get plastic buckling, and that can be a big problem. Particularly in a pipeline, you're going to send a pig down. You don't want an elastic dent to stop the pig from moving. That's a very bad thing. So you have to be careful about reduced structural stability. Also, most pipe segments are straight, but every now and again you want a bend, and often they're cold bent on site. And again, for a thinner wall pipe, it's more likely to buckle and wrinkle and even tear if you try to bend it too much. So again, it's possible cold bending problems. You have to be a bit more intelligent about the route that you take with your pipeline, but it is perfectly acceptable. So I'm not saying X80 doesn't work. I'm saying you have to be careful if you're using X80 compared to the lower grades. Now we'd like to have pipe that isn't made by the normal process of taking a strip, making it into a cylinder and then welding along the seam. And so there are processes around that can produce pipes in different ways. Seamless pipe, which is one of those, typically is used for smaller diameter pipes. So with a seamless pipe, you start off with a solid block of material, and you push your tool through the middle of it when it's hot, and you make it into a cylinder. And so that is not made from cold rolled steel, it's made from a forged billet. And therefore, the only control we have over microstructure is to normalise the pipe, which gives relatively low strength, or to quench and temper the pipe to get the small grain size. So the processing of the material to get the strength grade for seamless pipe is not the same as it is for the conventional pipe manufacture. But you can do it, and you can get good strength, and you can certainly make pipes with equivalent materials properties seamless and by the welded route. There are other processes like high frequency induction and spiral wound pipes where the welding doesn't have a longitudinal weld, it has a weld, as the spiral pipe's name implies, that goes along the length of the pipe. High frequency induction is very similar to a conventional welded pipe. It's just a different heating method. So there are variants, and often they come with a material which is specific for that particular variant of welding. So high frequency induction and spiral pipe is made from strip, which is usually supplied as coils. So there's some typical coils of steel strip here. ERW is electrical resistance welded pipe. High frequency induction is just one special case of electrical resistance welding. So I just wanted to say that there are different process variants that will achieve the same thing. And it's done on a semi-continuous basis. So the coils might have, a few hundred meters or at least 100 meters of material, and you can make maybe 20 or 30 meters of pipe in a single coil. And if you have a longer pipe and the equipment to do it, you can join the coils together, and then you can make a longer pipe. And people do that. You have to be careful when you actually make the coil that you don't introduce damage by the actual coiling process, and that's really done by controlling the coiling temperature. Otherwise, you get residual stresses and plastic deformation in the coil itself, which is not what you want. If you get good yield strengths, typically the elastic limit, RE, and the maximum stress, that's the ultimate tensile stress, which is RM in this diagram here, they're okay up to a certain temperature. But if we coil at a very high temperature, then those strengths will drop. And so this is a productivity question. If the strip is coming out of a strip mill very hot, do you coil it up straight away and get a lower strength, or do you allow it to cool a bit and then coil it up? That's the sort of thing that you have to ask. Question. But material can be delivered with the right sort of properties. Okay, so I've talked about the main materials and manufacturing related points about material selection for pipeline steels. What I want to talk about now is a little bit about selecting appropriate materials for corrosion service. You will get more information in the corrosion module, but this is really about the material selection aspects of that. So in my simplistic way of looking at things, we have sweet and sour corrosion that we have to worry about. And sweet corrosion is basically carbon dioxide and water, and it's like carbonic acid attacking the surface. And that's relatively benign, but it can be significant if there's a lot of CO2 in the gas, and that is not a problem unless there's water in the environment. And particularly when you've got products of combustion and things like that, and some of the processes, you might end up with a water content which is significant. So totally dry carbon dioxide isn't usually an issue. Damp carbon dioxide definitely is. The more serious case is sour corrosion. The product contains wet hydrogen sulfide. And this is why you have to analyse what's coming up off the wellhead and make sure that your materials are selected appropriately. What the hydrogen sulfide does is it poisons or sours the normal corrosion mechanism, and that leads to hydrogen being included in the material, leading to hydrogen embrittlement, hydrogen-induced cracking, or sometimes sulfide stress corrosion cracking. So that is a much more serious problem to deal with, and you need sometimes special materials to actually cope with that. Real life is not nice to us, so we always get a combination of those effects, and if both of them are present together, that's much harder to deal with than if it's just one or the other. That's just life, I'm afraid. More acidic, more low pH, chloride containing environments, then you get pitting as well as general corrosion, and that makes things worse. So seawater, if you've got that entrained in gas that's coming off the seabed, that's going to be worse than pure water that comes from a more benign source. And of course, if you've got a pipe in a marine environment, the outside might see this corrosion and the inside might see corrosion from the product, and there could be two different processes taking place on the inside and the outside of the pipe, which is why most pipelines are painted to protect from atmospheric corrosion. Okay. So sweet CO2 corrosion needs no tensile stress, just carbon dioxide and water. And one of the easiest ways to control it is to dry out the product. That is possible, but very unlikely, because that adds to cost. So the next thing is to live with the corrosion. So if the pipe needs to be 5 millimeters thick for stress, we'll put a corrosion allowance of 3 millimeters on it and increase the pipe wall thickness, and accept that over the lifetime of the asset, the pipe wall thickness is going to be gradually getting less. And that's often used. And then if you're really worried about it, if the rates are very high, if there's a high amount of CO2 in the product, you can choose to make the pipe out of corrosion-resistant alloys. This is the sort of thing that happens in refineries and in processing plant. It's less likely to happen in pipelines, but it does happen in some cases. Sour corrosion, particularly hydrogen-induced cracking, needs no tensile stress, just, again, hydrogen sulfide in a wet environment. Again, we dry the product, and there are steels which have been developed which are specifically resistant to sour corrosion. Sour stress corrosion cracking needs a tensile stress. That can be a residual stress or an applied stress. Again, it needs H2S, a wet environment, and the material has to have a certain hardness. So the higher hardness, more brittle materials will tend to be more susceptible. So we can control that by using low carbon equivalent steels, or we can use post-weld heat treatments to reduce the stress. The reason that I say, welds here, is if you imagine a weld between two pieces of pipe, the pipes are cold, the metal that you're depositing is hot, it will contract as it cools down to room temperature, and it will pull against the pipes. So most welds are in a state of tensile stress, which can be very, very high. It can be almost up to, or exceeding in some cases, the yield stress of the metal. So the region around the weld automatically has tensile stress because the pipes themselves don't move and the metal is fixed. If the pipes are allowed to move closer together, that can be reduced, but you can never get it down to zero. So that tends to mean that the weld region is the most susceptible to this stress corrosion cracking mechanism. So we want to use the low carbon equivalent steels and careful welding procedures to reduce the hardness, to reduce the susceptibility of the material to that cracking. Rough rule of thumb for weld heat affected zones is if the hardness goes much above 400 Brunel or 400 Vickers, then you've got a problem. And if it's less than that, then you're probably okay. And that's equivalent to a carbon steel with just 0.4% carbon, or a carbon equivalent of about 0.4 to 0.5, which you could see in the X80 standards over there. So the mechanism of hydrogen-induced cracking is complex. You tend to find that there are corrosion reactions which can produce corrosion ions. So if H2S arrives at the surface, it can be split to H plus and HS minus. And if you can get an electron from somewhere, from the metal generally, you can turn an H plus into a hydrogen atom. And a hydrogen atom is very small, smaller than the gaps between the iron atoms in steel. So hydrogen may escape into the gas phase, it may go into a sulfide layer or something like that, but often it diffuses into the material as H atom. And that hydrogen will collect. It collects in cracks, it collects around inclusions, it can collect near the surface at a crack, and the pressure builds up so that it pushes the surface upwards and you get what's called a blister. That hydrogen, therefore, reduces the toughness of the material. It makes cracking more likely. Now, for a long time, it was thought that hydrogen just collected in these cracks and defects and opened the defects up and made the defects more susceptible to cracking. And there is a good part of hydrogen-induced cracking which is due to that mechanism. But if you just take a piece of steel with no defects in, a perfect piece of steel, and you charge it with hydrogen, by whatever method you like to use, electrochemical methods, and you measure the fracture energy, you will find that hydrogen reduces the fracture energy of steel. And the reason for that is the hydrogen fits in the gap and it slightly affects the bonding around that gap. So the atoms are slightly weaker bonded, and then that will give you a higher chance that once a crack forms it will propagate through the material more easily. Has that been proved? Well, it's very difficult to find totally defect-free material. So it's been proved in the computer, but it's not necessarily something you can prove outside the computer. And which of the balance of these mechanisms is not sure at the moment. But hydrogen is bad news, basically, inside the material. That is definitely true. If you go to many industries and you have a failure, you have something that's cracked, and you have a look at it, and you do analysis, and you can't think why it's cracked, there'll always be some old timer in the corner who will say, oh, it's hydrogen-induced cracking. It's hydrogen embrittlement. And it's kind of the catch-all description for a failure we don't understand. And the reason for that is it's very difficult to analyse how much hydrogen is present in a material and analyse whether hydrogen is the cause or not. Detecting hydrogen is difficult by most modern methods. So because you can't analyse for it, you can't prove it is or it isn't, it tends to be the default explanation for things you don't understand. So I'm sure not every failure is due to hydrogen embrittlement, but since we can't measure the hydrogen, it's as good an explanation as any for failures we can't understand. But in the case of material where we're handling CO2 and hydrogen sulfide, in particular in hydrogen sulfide, there are clear corrosion reactions which will create hydrogen, and that hydrogen can diffuse into the material. So it's a very likely explanation, and it's fairly well proven. So what happens? Well, wet gas with hydrogen sulfide. This is quite obvious. There was a lamination in the middle. Remember the steel making process? We ended up with a defect in the middle of the thing. Rolled down, we still got the defect in the middle of the pipe, charged up with hydrogen. It fills with hydrogen. The hydrogen pressure is now inside a very long, thin pressure vessel, and it just pushes the surfaces up. And then we get high bending stresses on the surface here, and the tensile crack goes through to let the hydrogen out. Very clear. That's the sort of thing you can do in the lab every day. It's not the sort of thing that you can check for when you're looking outside. What you can see, though, when you measure it is these stepped cracks. And that's very symptomatic of hydrogen because the hydrogen is collected in these inclusion layers, and then the crack just links them all up. And around the world, particularly around the toe of the world, that's that part here, in the heat-affected zone, you'll see these cracks running in. There's lots of defects in these regions here, and lots of defects in the weld metal. The crack starts at the surface and tends to run inside, depending on what you've got. And remember that you get a residual tensile stress in this direction due to the cooling. So that's why it opens those cracks up almost perpendicular to the surface of the material. So when we're talking about selecting materials for the application. We've talked about strength and toughness and weldability. They're not the only criteria that you have to think about. You have to think about corrosion and the longer term service as well. But there are simple solutions. If the corrosion is not too bad, just making the pipe a bit thicker using a corrosion allowance is the way that most people would go. It's only as we go into more difficult fields with higher sulfur contents and things that these more difficult analyses become necessary, and we have a driving force towards other steels and even nickel alloys when things are very bad. So at the next lecture next week, I want to talk a bit more about these more corrosive environments, but I don't want you to think that every pipe is like this. They are in the minority of pipes, but there are occasions where you need them, and you should have at least a basic knowledge of what you've got to choose those sorts of materials, and that will be next week. I sent an email out to everybody to say the lecture tomorrow that Professor Gibson was going to do is cancelled. He'll start his lectures next Friday. Okay?